Okay, so welcome everyone. Thanks a lot for joining us today. It's our pleasure today to have Kirill Krasnov from University of Nottingham, and he will tell us about Urbantke metric and spinors.
Okay, thank you. Thank you for the opportunity. So first of all, I'm talking about somewhat exotic geometry here. And so let me start with some very general motivational remarks. If I can change the slides, yes. So we now know that gravity is best described as geometry of space-time, as dynamical geometry. But also after 100 years of work of mathematicians, we now understand that geometry or metric geometry is not the only possible one. And well, the simplest way to think about it is that metric tensor is just a tensor you can put on a manifold. And of course, there are many other tensors. Of course, not all of them are interesting, but for example, one can play the game of symplectic geometry, or in higher dimensions, one can put differential forms and study the associated geometry. So definitely metric geometry is not the only possible one. And because of this, it's possible that we don't yet know what the right geometric language to describe the universe is. This is one motivation of what I'll be explaining. And another motivation comes from a natural question that one can ask: what is special about geometry in four space-time dimensions? From the point of view of Riemannian geometry, there is nothing really special, but we actually know that if you, as it will become clear in my talk, if you think about four-dimensional geometry in a different way, then four is a very special dimension. Okay, so let's proceed. My plan is that I'll start by explaining this four-dimensional phenomena, Urbantke formula, self-duality, and all that, and the associated Plebansky formalism for GR. Then I'll talk about geometry of three forms in 7D, and finally I'll connect all that to geometry of spinors in 14 dimensions. So let's start with Plebansky formalism. We know that in any dimension, one can take square root of the metric, and so frame or vielbein is such a square root, and we can do geometry of frames rather than geometry of metrics, and this is very useful way of thinking. In four space-time dimensions, something extraordinary happens, something very, very special. We can take cube root of a metric, and this is the content of this Urbantke formula, so let me explain it briefly. One can describe metric by a triple of two forms. So explicitly, how does it work? We take BI, I is 1, 2, 3, so it's a triple of two forms. And then, well, the miracle is that having such a triple, one can construct a natural metric out of it. This is how it works. So the left-hand side describes the metric contraction of two vector fields, psi and eta. And it's this metric contraction times the volume form for the metric. The right-hand side is constructed like this. You insert one of the vector fields into the two form. This is a one form. Another vector field into the two form. That's another. Well, actually, this is a triple of one forms. This is a triple of one forms, and this is a triple of two forms. You watch them all together. This is the top form, and you take epsilon ijk. So basically, it's enough to consider here indices 1, 2, and 3. So it's clear that the right-hand side is a top form, and it's also symmetric in psi eta. So it gives you symmetric pairing of psi and eta, which is the metric, and you need to correct this formula for the fact that the right-hand side is a volume form. This is why you multiply it by the volume. Okay, this is the algebraic construction. So what is the significance of all this, and why does it work? So let me explain this. But first, maybe before I explain what is the geometry of that formula, let me mention that there is a formalism for dynamics of GR that you can base on this observation. This is the Plebansky formalism, Plebansky action. So this action is a functional of two forms, of a triple of two forms of the connection, SO3 connection. You see, it's a triple of two forms, so we naturally have SO3 acting on the triple, on the internal index, on the index I. And then it's a functional of Lagrange multiplier field as well. That's the action. So F, I, A are curvature two forms. Psi, I, J are trace-free Lagrange multipliers. If we vary with respect to these trace-free Lagrange multipliers, we get this equation. B wedge B is proportional to delta Ij. And these are 5 equations because we just say that it's proportional to rather than equal. So these are 5 algebraic constraints on the 18 variables in B. Right, B is 3 two forms, so altogether they need 18 numbers to be described. So it's 5 on 18, which leaves 13 parameters, or 13 variables in BI after this constraint is imposed. And these 13 really should be thought of as metric plus the frame, kind of the orientation of the frame of the triple of these B's. But we'll see how this happens. And then, so why is this related to GR? The first proposition is that when this constraint, when these equations on B hold, then SO3 connection that satisfies the covariant derivative of BI is equal to 0 equation, which is the Euler-Lagrange equation obtained by varying this action with respect to A. So this connection, which is algebraically obtainable in terms of derivatives of B, but this connection coincides with the self-dual part of the Levi-Civita connection for the Urbantke metric. Okay, so why? This is a sketch of the proof. When these algebraic constraints on B hold, B is metric, namely it is constructible from the frame. And it's actually just the self-dual part of the 6 two forms constructible from the frame. So that's one statement. And then, therefore, this equation, when B is of this form, this equation just becomes, or becomes equivalent to the fact that A is a self-dual part of Levi-Civita connection preserving the frame. So that's a sketch of the proof. Then another simple fact is that when both algebraic constraints on B hold and connection is compatible with the B, then this equation, F(A) on the curvature is blah, blah, blah in terms of B. This is the equation one obtains by varying that Lagrangian with respect to B. These are just nothing else but Einstein equations for the Urbantke metric. And sketch of the proof of this is that this equation, when A is a self-dual part of the spin connection, this equation says that the self-dual part of the curvature is self-dual as a two-form, because BIs are just self-dual two forms for Urbantke metric. And this is one of the possible ways to state the Einstein condition in 4D. So this is a sketch. If this formalism is not familiar to you, well, then it's probably difficult to understand everything I said, but at least as a sketch, I hope it's useful. The main point, of course, is that it's possible to trade metric for the triple of two forms, and it's possible to build a dynamical formalism for GR based on this. Now let me explain geometry of the Urbantke formula. Geometrically, what Urbantke formula does, it recovers the metric from the knowledge of which two forms are self-dual. So the way it works is that having a triple of two forms, one declares these two forms to be self-dual with respect to some metric. And this gives you enough information to recover the metric. So this is the content of this proposition. In 4D, the knowledge of which two forms are self-dual determines the conformal metric uniquely. The sketch of the proof of this is that if we start with a metric in 4 dimensions, then we can talk about the space of self-dual two forms for this metric. This is a three-dimensional subspace in the space of two forms. And then one can consider the restriction of the wedge product on two forms. So that we have a wedge product metric on lambda 2m. We can restrict it to lambda plus g. Concretely, we can take some basis in the space of self-dual two forms, evaluate bi by j, and we get a metric in lambda plus g. This metric characterizes the signature, or properties of this metric correlate with the signature. When G is Riemannian, this wedge product metric restricted to lambda plus is definite. When the metric is split signature, this metric on self-dual two forms is indefinite, so 1 plus 2 minuses. And when the metric one starts from is Lawrencian, then the metric one gets is complex, but then one gets an additional property that self-dual two forms are wedge orthogonal to anti-self-dual or to complex conjugates of self-dual two forms. So in Lawrencian signature, self-dual two forms are complex, but they're wedge product orthogonal to their complex conjugates. So this is what happens if one starts with the metric and then considers self-dual two forms. But the point is that it's also possible to go the other direction. If one starts with some three-dimensional subspace in the space of two forms, such that the restriction of the conformal wedge product metric on lambda 2, so it should be lambda plus here. So we start with some three-dimensional subspace, and then we consider a restriction of the wedge product metric on this lambda plus. It can be either definite, indefinite, or complex. There is just no other possibilities. And then Urbantke, the fact is that Urbantke formula based on this triple of two forms in lambda plus gives a metric. In here it's up to scaling, but scaling can also be fixed. That is Riemannian in the case of definite metric arising on lambda plus, split in the case of indefinite, and complex, and Lawrencian in the case of complex and satisfying this reality condition. Another way to think about all this is via isomorphism of homogeneous group spaces. One can see that what is happening here is it relies on these isomorphisms. So first of all, we have the space of two forms in 4 dimensions is a 6-dimensional space, and the wedge product metric on it is signature 3, 3. And then, so having the space of two forms with a metric on it reduces the group to the orthogonal group with signature 3, 3. Then selecting subspace, 3-dimensional subspace on which the metric is definite, is choosing point in this Grassmannian. So this the stabilizer of such a 3-dimensional plane is SO3 cross SO3. It's SO3 rotating in the plane and another SO3 rotating in the orthogonal plane. And then SO3 is the same as SL for R. And SO3 is the same as SO4. But this, so the left-hand side here is a choice of a 3-plane in 6 dimensions. The right-hand side is a space of conformal metrics, conformal Riemannian metrics in 4 dimensions. So this is why indeed a choice of a triple of 2 forms gives a conformal metric. And the same happens for other signatures as well. Okay, so this is a recap of the geometry of 2 forms, of triples of 2 forms in 4 dimensions. And then the question is, how should one think about all these facts? Is this, so this is beautiful geometry, one can base description of GR on it, but what is the role of all this in the wider scheme of things? And this is where the 7-dimensional observations come in. So the main point here is that everything I said about geometry in 4D can be seen arising from something happening in 7 dimensions. So the facts, the geometric facts here are, if we have a generic 3 form in 7 dimensions, this determines a metric in 7 dimensions. And there is a similar cube root formula. So let C be 3 form in 7 dimensions, then we can construct a metric depending on C as follows. It's the metric contraction of 2 vector fields multiplied by the volume form of the metric is 1/6 of you insert the vector field into C. This is a 2 form, another vector field into C. This is another 2 form. Then wedge with C, it's a top form. And then we get, and moreover, this is a top form, which is symmetric in psi eta. So indeed, this defines some symmetric pairing of psi eta, which is just the metric corrected by the volume factor. This formula was discovered very long time ago. It's more than a century old. Again, it looks kind of exotic, and probably it is exotic. You'll see the geometry related to it is exotic. So let me describe it. But what is important for us is that it's not only analogous to the Urbantke formula, it actually contains the Urbantke formula. And indeed, just by, well, it's kind of the fact that it's a cube, it's something cubic in C appearing on the right-hand side, and the structure of the formula suggests that it must be related to Urbantke. And indeed, it is, as I said, it contains Urbantke. So let's take R3 bundle over M4, choose a basis along the fiber directions, and then start with a triple of 2 forms on M4, these B's. Then let's build a 3 form of this sort. So we take E1, E2, E3 along the fiber directions. This is a volume form along the fiber direction. And then E1, B1 plus blah, blah, blah. So it's clearly a 3 form in the total space. And then it's a very simple calculation that this angle metric restricted to fibers is just Bi, Bj, which is a quantity we had appearing in the previous considerations in 4 dimensions. And then this formula, the metric restricted to 4 dimensions, is just the Urbantke formula.
Now the B's here are 2 forms over M4? Or?
Yeah, exactly.
That's before.
Yeah. So B's were exactly as in my previous considerations. And now I'm building a new object out of them. But this new object is, of course, I take M4, R3 on top of it. E1, E2, E3 are kind of 1 forms in those directions, right? So I'm building a 7-dimensional manifold here, which is just M4 cross R3. And I'm building a 3 form on it this way.
Sorry, is this the hot vibration?
Well, it's related to it, but here I'm doing something much more trivial than Hopf vibration. Hopf vibration would be it's S3 over S4, and then the total space would be S7. Here I'm just doing actually linear algebra. I'm working at a point or at the tangent space of a point. So I only care about what happens locally here.
Yeah, okay.
Because I just want to construct, to show how these local formulas arise. Yeah, so this is something much more trivial than, but of course it's related to Hopf vibration. So for example, on S7, there is a 3 form of this type naturally arising. And of course you can obtain the geometry of around S7 by taking this. So there is a certain canonical 3 form on S7. You put it into this formula and you get geometry of around S7. this way. Okay, so we see how four-dimensional story gets naturally embedded. One can add a little bit more to the statements or make the statement more precise. So the slightly more precise version of it is that if we take a real three form in 7 dimensions, and we take a general one, or stable. Three form is called general if it's appropriately non-degenerate. One way to state what non-degenerate is that the metric you obtain from this three form is non-degenerate. That's one can of course give another definition, but then it will be equivalent to this one. So let's just for us it's simpler to think that a three form is non-degenerate if the metric you obtain from it is non-degenerate. And this is a non-trivial condition because, for example, if you take some decomposable three form like E1, E2, E3, you will not get any non-degenerate metric out of it. So the three form we're talking about, if it's general, it's not decomposable. It's a sum of decomposable terms. So if we take such a generic real three form, then there are just two possible stabilizers of this three form in GL7. It turns out that, so this means that there are two possible types of a real three forms in 7 dimensions. The stabilizer of one of them is G2, and the other one is G2 prime. In the case of G2 stabilizer, the metric one obtains from GC is definite. For G2 prime, the metric one obtains is signature 4-3. So these are the only two things, or the only two metrics that can arise from real three forms in 7 dimensions. And so this is exotic because it is linked to octonions. To see the link, one can notice that such a generic three form in 7 dimensions, it identifies the tangent space at a point. So we're talking about vector space, we take a three form on it. And if this three form is generic, the three form identifies a vector space with imaginary octonions. Why? Well, we've seen that three form gives us a metric. So let's assume that this metric is definite, and then we have a metric on imaginary octonions, which is definite. But the three form also gives us a cross product, and this is this formula here. So you say that the cross product of two vectors, metric product with another vector, is just the insertion of these three vectors into the three form. It turns out that this definition, the properties of C are such that this definition makes sense, and indeed we get the cross product in 7 dimensions from C. And so indeed we have a C identified vector space with imaginary octonions, providing us both the metric and the cross product on it. And then one can think that the way Urbantke formula arises is by selecting a copy of imaginary quaternions in imaginary octonions. And indeed, the triple of two forms in 4D, when they satisfy this BI, BJ proportional to delta IJ, if you take such a triple, you define a metric that B's give you, you use the metric to raise one of the indices of B, and you get a triple of endomorphisms of your 4-dimensional space. And then this triple will satisfy the algebra of imaginary quaternions. So this is why it's all linked. The B's was really giving us quaternionic structure in 4 dimensions. The C is giving us octonionic structure in 7 dimensions, and then the link between the two is that we're doing dimensional reduction. We're selecting copy of imaginary quaternions and imaginary octonions, and then this is why we recover Urbantke formula. So this is why it's all related. So this is what set here. Urbantke formula in 4D is just the angle formula in 7D plus dimensional reduction. Okay, so then we have still the question how to think about all this. It seems that it's very exotic, and is there any other way, or well, where do you put all this? It's beautiful geometry, but is it just completely exceptional, related to octonions and to nothing else, or is there some more general way of understanding all these phenomena? And another question, which is open question, one can get only Riemannian or split signature for D metrics from real free forms in 7D. And then it's very natural to ask, is there any interpretation, 7D or something like that, interpretation of the Lawrencian 4D metrics? Lawrencian 4D metrics, the associated two forms are complex, so the associated three forms would also need to be complex, and then is there some geometry, natural geometry that describes all this? This is not really understood at present, but it's a very natural question to ask. But so let me, for the rest of my talk, let me provide some further interpretation to this 4D and 7D phenomena. I want to convince you that there is at least one natural interpretation, and this is interpretation coming from spinors. So let me see how much time we have. Yeah, I'm fine. I'm switching gears completely now, and I'll be talking about spinors, some generalities about spinors. Let's start with a vector space equipped with some metric, real metric of given signature, RS. And you'll see I don't want to play my game over complex numbers. I want real metrics. So it's R plus SS minuses. Then there is a Clifford algebra that can be defined. This is generated by vectors in V subject to this relation. Then a Clifford algebra, it's a fundamental representation of dimension 2 R plus S over 2 is called spinor representation. For simplicity, I'll assume that R plus S is even, because the odd dimensional case is related to the previous even dimensional case. So it's very easily obtainable once you understand the even dimensional spinors. You can get the odd dimensional ones as well. Then we have a spin group. One way to define it is to say that it's generated by even number of products of Clifford algebra elements of norm plus minus 1. Then in even dimensions, spinors are not an irreducible representation. They split into positive and negative spinors. Okay, this is all familiar, at least in 4 dimensions, right? When we have Weil spinors of 2 types. And then further generalities is that we always have an inner product on spinors. Its properties depend only on n and not on the signature. So for example, when in 2 dimensions, so spin 2, spinors, the spinor product, inner product, pairs positive with negative. That's what it does. In 4 dimensions, we have a pairing of Weil with Weil, and it's anti-symmetric. This is familiar. This is the epsilon tensor, 2-dimensional epsilon tensor spinors, Weil spinors in 4 dimensions. In 3 dimensions, we pair again positive with negative. In 4 dimensions, we pair Weil with Weil, but it becomes symmetric. And then this pattern repeats itself with this periodicity. So the next, if you go to 10, you'll get S plus to S minus again. Okay, this is, we also have signature-dependent charge conjugation. This is antilinear operator on spinors that commutes with all transformations from spin and squares either to plus or minus 1. And the property of this guy depends on the signature. So when the signature, if I'm in even dimensions, then my signature is always even, R minus S is even. So when K is odd, then my star operator will pair S plus to S minus and square to plus 1, or can be chosen to square to plus 1. And then when K is multiple of 2, it will square to minus 1 and pair vial to vial. When K is multiple of 4, it will square to plus 1 and pair vial to vial. So in particular, in this case, when K is multiple of 4, we can define Majorana vial spinors. In this case, we can define Majorana spinors. So for example, this is a situation with Lawrence group. With Lawrence group 3, 1, 3 minus 1 is 2, so K is 1, and then our star operator maps positive spinors to negative spinors. It's a complex conjugation. We usually describe it as a complex conjugation, which maps primed to unprimed, and then we have a notion of Majorana spinor. It's a Dirac spinor that is real. That is the eigen state of the star operator. But for example, for spin 8, one can define Majorana vial spinors because one has this star that squares to plus 1. Okay, this is some very general things. Then another generality is that you can think about spinors as giving you square root of geometry. So in what sense? Given a spinor, one can produce a list of geometric objects in your vector space from the spinor. How does it work? Well, you take a spinor, and for me, spinor is always vial spinor here, because you've seen that inner products were either, it was always pairing between vial spinors, either with vial of the same helicity or two vial spinors of different helicities, but it's always pairing between, or it can always be described as pairing between vial spinors. So I take a vial spinor, another copy of the same vial spinor, and then I insert a bunch of gamma matrices in between. Of course, the number of copies I should insert depends on dimension. If I had a pairing that only paired plus with minus, then I can only insert odd number here, because my odd number of gamma matrices will map S plus to S minus. And then if my pairing is S plus to S minus, then only an odd number can be inserted. But so it depends on dimension, how many gamma matrices I can insert. And it's clear that I'm producing by this construction an object which is anti-symmetric tensor in my RS in the original vector space, because these indices should be taken to be distinct, right? And by properties of Clifford algebra, if they're not anti-symmetrized, then they're reducible to some lower dimensional object, and so it's not interesting. The independent objects, I should always consider anti-symmetrization of all these indices, so they are anti-symmetric tensors. Okay, so spinors define as these anti-symmetric tensors. If one has a star operator, one also has this other type of anti-symmetric tensors arising. One can start building them using the complex conjugate of the spinor as well. So these tensors, the availability of them doesn't depend on the signature. These ones depend on the signature. So very familiar example to you all is that if we have a vial spinor in a Lawrence group, then we have indeed such tensors. If we insert one gamma matrix between psi and psi star, psi star is spinor of opposite type. If this is S plus, psi star is in S minus, and then I can insert one gamma matrix in between. I get a vector. This is this null vector produced by the spinor. If I take while, then I can insert an even number of gamma matrices. I cannot insert no gamma matrices because the pairing in 4 dimensions is antisymmetric, so psi is 0. But I can insert 2 gamma matrices and I'll get a 2 form. These 2 form will be self-dual, and well, in spinor notations is this guy. It's a self-dual 2 form built from the spinor. So spinor can be viewed as a square root of geometry in the sense I explained, and this referring to a spinor as a square root of geometry is actually, well, it's a statement that I took from talk by Michael Aitia, What is a Spinor? You can watch it on YouTube. This is a interesting talk. So we see that spinors produce lots of antisymmetric tensors. Okay, now again some generalities about spinors. The easiest possible spinors to describe are called pure spinors. And why do I talk about them now? Because basically I want to argue that in lower dimensions, all spinors are simple, in the sense that they are the simplest possible type. All spinors are these pure spinors. So you get a new type of spinors in higher dimensions, and you get more and more interesting stuff happening in higher dimensions, and we'll be able to link the beginning of my talk with the geometry that starts to arise in higher dimensions. So let's see how all this happens. The definition of pure spinor is as follows. If you consider a spinor, there will be some set of gamma matrices that annihilated in the sense that gamma matrices act. If you think about spinor as a column, gamma matrix is a matrix, you act with a gamma matrix on the spinor, you get a 0. So there is typically some subset of gamma matrices annihilating it. So we can introduce a notion of annihilator subspace of a spinor. It's better to introduce this notion for the Weil spinor because Weil spinors have non-trivial annihilator subspaces. So we define M psi as a subspace of a vector space that annihilates psi when acted on psi via the Clifford product. Then one can show that the maximal dimension of this annihilator subspace can be half the dimension in which you're in. Remember, R plus S is 2n. So it's smaller or equal than n. And so spinors with this maximal annihilator are called pure or simple in Cartan's terminology. As I said, pure spinors are always Weil. And then pure spinors can be characterized very nicely. And this is the original observation by Cartan. The only non-vanishing geometric objects or geometric object that can be built from a pure spinor, and here we're talking about not using the complex conjugate, just pure spinor is in itself, is the top form. Remember, we can insert a number of gamma matrices. So if you work with a pure spinor, the only thing that is non-zero is the maximal possible number of gamma matrices, namely half, well, n of them, so half the dimension. And then the statement is that this n form is decomposable automatically and is given by the wedge product of the n directions from the annihilator of the spinor. And this is if and only if statement. So it turns out that in the other way, the statement is also true if the only non-vanishing antisymmetric tensor that you can produce from a spinor is this top one, and all the previous ones with lower number of gamma matrices vanish, then the spinor is pure. So one can say that pure spinors satisfy lots of quadratic constraints, because these tensors that are produced from psi's are quadratic in psi. So pure spinors satisfy some quadratic constraints. Of course, more general objects can be constructed using psi star, but this depends on the signature. This statement is signature independent. It just depends on dimension. And then, so because of this characterization, pure spinors are the simplest spinors to understand. Properties are the same in any dimension. And then a simple fact is that in dimension smaller or equal than 6, so n is smaller or equal than 3, all spinors are pure. And this follows just by the fact that you go dimension by dimension, and you see that indeed in dimensions up to 6, the only object you can produce is this top form, or half and gamma matrices are inserted. Everything else vanishes just by properties of the spinor pairing in lower dimensions and so on. So indeed, so up to dimension 6, everything is as simple as it can be. The first dimension where we see non-pure spinors is n equal to 4, or spin 8, and of course spin 7, spin 9 as well, but the first even dimension is spin 8. And then just to understand what kind of spinors are non-pure, so it turns out that there are essentially two main types of spinors. There are pure spinors in this dimension, and they're complex, or, well, maybe I shouldn't talk about complexity here, but so they're pure spinors, and the Majorana-Weil spinors satisfying this Majorana condition that are possible, that becomes possible in 8 dimensions. And these Majorana-Weil spinors are not simple or not pure, and they can be linked to octonions, or they can, in fact, be identified with octonions. So it's interesting that the first time we see non-pure spinors arising, they are octonions. So this tells you that non-pure spinors are interesting. They're more interesting. They give you more interesting geometry than the pure ones do. In kind of in more generality, or if we talk about spinors that are not necessarily pure, any spinor can be represented as a linear combination of pure. So pure spinors in general give you basis in the space of all spinors. And you need more and more pure spinors the higher you go up in dimension. And the geometry becomes more interesting as one goes up. So this is some quick discussion of what happens if you go high in dimension. I already told you that for spin 8, non-pure means spinor is octonion, and then there is some octonionic geometry arising. For spin 10, a generic spinor defines a pair of real vectors, or a complex vector in R10, and a complex structure on R8 that is orthogonal to this pair of real vectors. So you see, this is what the general spinor of spin 10 gives you. It gives some interesting geometry. In higher dimensions, things are even more complicated to understand, or they are not really understood. The classification becomes difficult. And in higher dimensions, so first of all, only dimension 12, 14, and 16 are understood. And only Majorana-Weil spinors in these dimensions are understood. General spinors are not even understood beyond 10 dimensions. So So for example, in 12 dimensions, one can take this 6-6 case, which admits Majorana spinors. As I said, you need to either play the game over complex numbers or work with Majorana Weil spinors to obtain classification. And then Majorana Weil spinors do not exist in all signatures, but in this one they do exist. And then generic Majorana Weil spinor is a sum of two pure spinors, and it defines complex or paracomplex structure on R66. That's the geometry that a generic spinor gives you. The way this works is that one takes spinor, inserts two gamma matrices. Between them, if this was a pure spinor, this would vanish. But now we take a generic spinor, which is non-pure. So one gets a two form on RC6. One raises the index, one of the indices of these two forms using the metric. You get an endomorphism of R66 this way, and then a miracle, or maybe not a miracle, but the fact that this endomorphism squares to a multiple of the identity. So you get this endomorphism, which is either, well, it squares to either +1, and then gives you paracomplex structure, or -1, and gives you complex structure on RC6. So that's what you get from spinors in 12 dimensions, from real spinors in 12. From spinors in 14 dimensions, and this will be related to Urbantke formula eventually. So the only geometric objects that can be constructed from a real spinor in 14 dimensions are 3 form and 7 form. This will be non-vanishing for non-pure spinors. And then one takes 3 form, raises 2 indices, contracts them, and then one gets an endomorphism of R77. This again can square either to +1 or -1. And in fact, when the spinor one starts from is generic, this is what will happen. You get this endomorphism becomes non-degenerate, and it will square it either to plus identity or minus identity. But this endomorphism turns out to be compatible with the metric in a strange way. It's a different compatibility with the metric as compared to the more standard one. So usually we have the complex structure is compatible with the metric like this. Paracomplex structure is compatible with the metric with a minus sign. But in this complex and paracomplex structures arising in 14 dimensions, the signs here are reversed. And then the eigenspaces of these structures are not null. And so what the spinor gives you this endomorphism K. When it squares to +1, it splits R77 into eigens directions of K. The metric restricted to these factors is not null. You get 2 metrics. And then the stabilizer, one finds that the stabilizer of the generic spinor is either G2, G2, or G2 prime, G2 prime. But what is more important for me is that this is the way that formula for the metric out of a 3 form in 7 dimension can be seen to arise. And let me explain this. So this is one of the last slides. To see how this is happening, one must resort to another construction, which I didn't explain, but let me state it as a fact. So if you work with spin groups of NN, then Majorana Weil spinors of such spin N can be described as even or odd degree in homogeneous differential forms in half the dimension. So for spin 7,7, the generic odd spinor is C1, C3, C5, C7, in 7 dimensions. It's a simple construction to see this, but I don't really want to explain it. Well, just take it as a fact that spinors are such inhomogeneous differential forms in half the dimension. And then another claim is that a generic Majorana-Weil spinor of 7,7 is in the orbit of this spinor. So basically, by spin 7,7 action, one can kill this term, and only remain with C3 and the 7 form. And then for generic spinor, this C3 must be generic in 7 dimensions, as we discussed. And then there is some coefficient that can arise here. And what is important is the sign of this coefficient. Because in principle, one can start rescaling things and then one can get rid of the number here, but one cannot get rid of the sign. The sign here, the relative sign, is important. And then when this number here is negative, by a construction that I explained, you start with a spinor, you construct 3 form in 14 dimensions, you construct some endomorphism from its square, and then if this sign is negative, then this is a paracomplex structure. It splits 7,7 into 2 orthogonal subspaces. Both are R7. The metric on them is non-vanishing. The restriction of the big metric in 14 dimensions to these 2 spaces is non-vanishing. And in fact, for such a simple spinor, you get the same metric on both of these factors. And so this explains how a metric in 7 dimensions arises from a 3 form in 7 dimensions. It turns out that this is the same story that we talked about before. And there is also the case when one can have a complex structure, and then well, let me not talk about that any further. Okay, so the claim is that the metric that is induced on plus minus 1 eigenspaces of some endomorphism that is built from the spinor is the Engel metric in 7D constructed from the 3 form in 7D. So this explains that the metric from 3 forms in 7D has its origin in the geometry of spinors in 14D. This was the main fact, the main geometric fact that I wanted to explain. So let me summarize. I talked about geometry of triples of 2 forms in 4D and how they define metrics. And then I explained how this story is embedded into the story of geometry of 3 forms in 7D and how this can define metric in 7D and how bidimensional reduction we can get to this story. But then all this has spinorial origin, and probably this is the right way to think about where all this is coming from. So the spinorial origin is that the idea is that we study spinors in general, and then we go higher and higher in dimension and see what is possible. What is the geometric objects that can be constructed from a spinor? Spinor defines antisymmetric tensors, but in lower dimensions, you can't get any interesting symmetric tensors from these antisymmetric tensors. Right? So you can take antisymmetric tensors, start contracting indices and getting some. For example, you can take 3 form, contract pair of indices. You'll get some symmetric tensor this way, but up to 14 dimensions, you don't get anything interesting this way. And in 14 dimensions, you start getting interesting tensors, interesting symmetric tensors arising this way. And this is how the formula for the metric out of the 3 form appears. This seems to be the origin of all these mysterious phenomena in lower dimensions. Okay, and let me end with the question. So all this is linear algebra. it's understood what kind of differential geometry or what kind of differential equations one can write. Just in this case, there is also some understanding, there is some story of some natural differential equations one can impose on 3-form in 7D. This story is, well, it seems to be less understood. And so let me end with the question, what kind of natural differential geometry is related to all this? Okay, thank you.
Thanks a lot, Kirill, for the nice talk. Okay, so we have time for some questions. Itera, yeah.
Yeah, can I ask a question?
Yeah.
Thanks for the talk, Kirill. I'm sorry I missed the beginning of the talk. This is all intriguing geometry. I was wondering if there's something very special about 7D, or if there might be other generalization of the Urbantke formula from other dimensions. Is it really because there's all the octonionic structure and all that?
It seems that, yeah, Urbantke formula is very much about, Urbantke formula is really about quaternions. So that triple is, they're really imaginary quaternions. This is why Urbantke formula works. So it's imaginary quaternions in 4D, imaginary octonions in 7D, and you see 14D is also special, but 14 is 2 times 7, so this is why it's special. It's again octonionic. It seems that this stuff is related to octonions. I don't know any natural other generalization of all this. It seems that it's all octonionic.
Okay, and I was wondering where you're going with all this, because it's very nice geometry, but are you going towards some formulation of general relativity from some theory of 3 forms in 7D, or some new type of generalization of modified gravity theories? Or, I mean, what do you have in mind?
Yeah, this is of course the right question. So what I studied some years ago was so there is a fact in 4D, which is a strange fact. The fact is that one can modify general relativity in 4 dimensions rather non-trivially, in the sense that you modify dynamics of metrics, but you don't introduce any degrees of freedom. So this is, it turns out that in 4D, GR can be modified without adding degrees of freedom. This goes counter all of our intuition about GR, because we have uniqueness statements about GR. But it turns out that the catch is that these modifications are only possible in split and Euclidean signature. So it turns out that you can modify Euclidean and split signature GR without degrees of freedom. By degrees of freedom, I mean, like, you think about initial value formulation, and this is a number of data at a point that you need to give for your equations. So one can talk about degrees of freedom also in Euclidean and split signatures. So one can modify GR in Euclidean split, but one cannot do it in Lawrencium, because in Lawrencium it's all this reality condition stuff that gets mixed in, but and this is why it doesn't work. But in Euclidean and split it is possible. And then it was a question, why, what's the role of this? Where does it all come from? So one interpretation that I was able to come up with is that these modified theories in 4D, they come up, they can be understood as dimensional reductions from something very natural in 7D. You start with 3 forms in 7D, you write very natural dynamical condition on this 3 form, you dimensionally reduce, you get these modifications in 4D. So that's why it all appears. And then for me, the question was, what's the role of Lawrencium Urbantke formula? As I explained in the beginning, there exists Lawrencium Urbantke formula, but there is no 7D interpretation of it, at least not the one people know of, definitely not with real 3 forms. One must take complex 3 forms, but then the geometry is, it must be complex 3 forms satisfying some reality conditions, and the geometry of this is not really understood. So this is one of the directions where I'm going. And I was interested in 14D. Maybe I was hoping that it will give me a hint for this Lawrencium story. So that's really the direction. I'm trying to understand. There is definitely Lawrencium Urbantke formula, but is there some high dimensional version, high dimensional way of thinking about it? That's one question. If yes, then I would expect that there is also some gravities, maybe modified gravity in 4D coming up from higher dimensions. But so this is one question, trying to think about gravity in 4D as coming up from something else, from higher dimensional geometry of a special type. And another observation that I was excited about, maybe it's even more speculative observation, but it turns out that if you take fermions of the standard model and you attach the Lorentz, so you take fermions of the standard model, they transform as a representation of spin 10, like one generation is a Weil spin of spin 10. You attach the Lorentz group to this spin 10, and then you can think about fermions of one generation of the standard model as Weil fermion of Lorentz group in 14 dimensions. So again, 14-dimensional spinors arise this way. And so I was playing with these two observations and tried to connect them with some observations on the way, but nothing concrete. So in general, I'm excited by the geometry of spinors in higher dimensions. And it seems that, as I said, spinors define geometry, and then maybe one can think, well, gravity is dynamics of geometry. Maybe one can code this geometry into spinors. That's the general direction that I'm exploring.
Okay, thanks.
Another question? Yeah, Hank?
Yeah, I have a rather naive question. So we define spinors using Clifford algebras, right, which are associative, but the Val Majorana spinors form an octonion, which is not associative. So I'm just wondering where that comes from.
Yes, that's a good question. So the way you code or the way you represent Clifford algebra in 8 dimensions using octonions, you use the operator of left multiplication by the octonion. So basically your gamma matrix is the operator of left multiplication by an octonion. And then these guys are associative simply because you prescribe the rule how you put the brackets. Left multiplication, right? It's a certain prescription for how you put the brackets. So you give a prescription that avoids the issue of non-associativity. If you want, it becomes associative because you specify how the brackets are located. If you want, we can think about it this way. So think about an octonion as a column, and then you take another octonion. So there is a procedure of multiplying this general octonion column by your octonion from the left. This is a matrix, right? You can encode it into 8 by 8 matrix. And of course, multiplication of matrices is associative. So
Okay, I see.
That's what you do.
Okay, thank you.
Okay, any more questions? And if not, I had maybe a last one. Actually related to Etera's question. I was wondering if there are reformulations of classical GR. Probably not in 4D, but in this higher dimensional case, 7D or 14D, using these Majorana-Weil spinors, like what we have in 4D.
but depends what kind of formulation you're asking for. So for example, there is something beautiful in 7D. Maybe I can explain that. So 3 form in 7D, you start with some generic 3 form in 7D. It defines you a metric. There is also notion of Hodge dual of this 3 form with respect to that metric. So it's a Hodge dual defined intrinsically by the 3 form itself. So there are 2 objects, 3 form and a 4 form. Then it turns out that you can impose equations that d of the 3 form, the usual exterior derivative on 3 form vanishes, and exterior derivative on the 3 form star vanishes. You impose these 2 equations.
Okay.
Then, well, it turns out that what these 2 equations imply is that the Riemann, well, so there is a metric constructed from the 3 form. So it turns out that these 2 equations imply that that metric is Ricci flat.
Okay.
So it gives you Einstein condition. Of course, they imply a bit more, but in particular, they imply that the metric is Ricci flat.
Oh, okay. So D of A and D of star.
D of C and D of C star is 0, is Ricci flatness. So that's, you see, you get, if you want, Einstein equations with 0 cosmological constant for free this way. But of course, where it comes from is that this 3 form in 7D is really metric plus a spinor, and the equations that you're imposing require that the spinor is parallel with respect to that metric.
Okay, yeah.
When you have a parallel spinor, you are Ricci flat.
So
that's how it all happens.
Yeah, that's okay.
Yeah.
Very intriguing here.
Yeah, but of course, this the general story that one can do geometry via spinors. It's well-known story, and there are many mathematicians exploring this kind of general land of geometry.
Yes.
One can do beautiful geometry and differential geometry using spinors.
And then above 14D, is there any hint that this pattern continues with some?
It's clear that 14D is some. So it's so 14 and 16 are related, like 7 and 8 are related. Both are in some sense octonionic, or at least spinors in 8 dimensions, while spinors are just octonions. Spinors in 14 dimensions, while spinors, one can think about them as bioctonion, octonion time octonion. It's 64-dimensional matrix. Spinors in 16 again can be described using octonions, kind of as 64, kind of 8x8 matrix plus another 8x8 matrix like this. And because of this octonionic description, they can be classified. And they have been classified. It's also interesting that spinors in 16D are related to E8, because E8 is just SO16 plus the Weil spinor of SO16. So they're very much related to E8, and this was used in the classification of spinors in 16 dimensions. Beyond 16D, it's a mess, because the main problem is the dimension of the spinor representation grows exponentially. So you have just too many possible types of spinors. Already in 14D and in 16D, it's a complicated classification. The simplest possible orbits are easy to describe, and they give you the most beautiful geometry. But there are lots of more degenerate orbits with no clear geometric interpretation.
Okay.
But yeah, kind of this in 14D, 16D, it's all clearly related to octonions. In higher dimensions, nobody knows. It's just it appears to be untactable at the moment. At least nobody has the right technique to classify it. But even understanding the geometry in those dimensions fully, it's sufficiently complicated so that it's not explored well enough. There are probably some simple, beautiful geometric facts that are still there, but still unknown.
And is it have people studied compactifications from say 7D to 4D? Is this
from 7D to 4D? It's not interesting, but so yeah, but well, the answer is yes. But what are the natural compactifications?
Yeah,
one can take so one definitely needs something 4-dimensional plus some internal space, right? And the idea is that you take spinor in this big space, you dimensionally reduce, and you get a bunch of spinors in 4 dimensions. The beauty of spinors is that when you take a big spinor and dimensionally reduce, you get spinors in lower dimensions. You don't get any other strange objects.
yeah, that's
the beauty of it. And this is why the idea that you can take kind of Minkowski plus internal space, and you will always get spinors of Minkowski starting from a spinor. This is why, for example, the particle content of one generation of the standard model can be encoded into just one Weil spinor in 14 dimensions.
yeah, because you
Weil
don't
spinor, you dimensionally reduce, you get all the spinors that you have in 4 dimensions.
yeah.
So that's the idea of dimensional reduction. It's a beautiful idea. It unifies everything that is there into just one object. But of course, what do you reduce on, and what is the dynamics of dimensional reduction? So people in string theory, they reduce on 7-dimensional manifolds because they have a natural 11-dimensional theory. They have an 11-dimensional supergravity. It's natural to reduce it to 4D on something 7-dimensional. But then if you reduce on 7-dimensional objects, then you cannot get chiral fermions in 4D if this space is non-singular.
Mm-hmm.
This is why you need to go to strange singular 7-dimensional manifolds.
Mm-hmm.
And it becomes not easy. And 7D as an internal space is the minimal dimension that you need to obtain the gauge group of the standard model. So 7 is minimal, but also not, and of course people were excited in the 80s that 7 is exactly what is needed to give you to 11, to get you to 11, where you have a natural theory.
Yeah.
But another game one can play is take 8 for the internal space. That's there is no natural 12-dimensional theory, but one can say, so what? Well, let's still do it. Maybe there is some theory that is just exist. Well, maybe there is something. So let's just explore it. But then in 8D, if you reduce on 8-dimensional theory, you can get chiral fermions in 4D if you reduce on 8. So that's a natural game. This requires spinors in 12 dimensions.
Mm-hmm.
But after some thinking about what kind of spinors you need, it turns out that one needs Majorana spinors, so kind of Weil plus its complex conjugate, 12D. But these Majorana spinors, it turns out that the easiest way of getting them is to take Majorana Weil in 14D and then take a complex structure, take two dimensions special, take an associated complex structure and reduce. So Majorana Weil in 14D is economical way of thinking about Majorana in 12D.
Mm-hmm.
This is how they can be motivated. So yes, one can do dimensional reduction. Dimensional reduction from 11 to 4 has been explored a lot. Dimensional reduction from 12 to 4, not too much, because there is no natural theory to start with.
Yeah.
Sorry, just to go back to like the question that about like higher spin geometries, like you really don't expect any periodicity in dimension, because I thought the KO groups have period 8, right?
Yeah, you expect periodicity in properties of Clifford algebra. Classification of Clifford algebra is periodic.
Yes.
But properties, well, not really, simply because you get this exponential growth in dimension of the spinors. So, well,
I see. Okay.
there is no periodicity. For example, if you go from 8 to 16, or maybe let's do something simpler. Let's go from 4 to 12. In 4, all spinors are pure. In 12, they're not. And well, you get very interesting geometry coming from non-pure spinors.
Mhm. Mhm. I see. Okay. Yeah, I guess Morita equivalence does throw things a lot. Like throw a lot of things away.
Well, it's just well, the Clifford algebra is repeating its classification. If you know what the Clifford algebra, the classification of Clifford algebra, all Clifford algebras are matrix algebras, or maybe two. I mean, sum of two matrix algebras in odd dimensions. Like in 7D, it's M8 plus M8, but in even dimensions, they're just matrix algebras, and they can be real, complex, quaternionic.
Yeah.
This repeats in dimension, but this is based only on availability of those star operator. Basically, the star operator tells you it's very much, its properties are very much related to classification of Clifford algebras. If it squares to -1, then it's quaternionic case. If it squares to +1, I think it's real. Well, yeah, it's I'm unable to reproduce it now, but it's basically related to the star operator.
Yeah, and I'm also interested in like, because here you introduced a dimensional reduction that kind of encapsulates the Urbantke formula, which is really interesting to me because that links to like general relativity, and also like the reason I mentioned hot vibrations because it generates this homotopy group, right, for the force sphere. And I'm just wondering, like, you do things locally, fine. You say that the half element 0, but what if it's 1, for example? Like, what happens to the geometry? Do you know?
In what sense? What happens to the geometry? So we have this 3 form on the 7th sphere.
Yeah, well, I'm just saying that the half vibration is not trivial, right? Because so like there's some non-trivial winding of the quaternions.
Yes.
Imaginary quaternions, sorry. Yeah. So the S3, right, in the fiber direction, there's non-trivial winding. So for example, you have I believe what really happens is E1, E2, E3, that's a local expression, but that's you can't like patch it globally on the S3. Yeah.
Well, so I'm not sure what the question is. It's true that there is this Hopf vibration, or we can think about S7 as S3 over S4. The reason for that is that S7 is, you think about it as sitting inside R8. R8 is 2 copies of quaternions, and then quaternion times quaternion complex conjugate, right? That's your Hopf projection. That's your, you can go from, like, if you take 2 complex numbers, you take complex number times complex number conjugate, Z1, Z2 star. This has some invariance. You can multiply those complex numbers by phase. This complex number doesn't change. The same you can do with quaternions, and this is your Hopf vibration. You can go from 2 quaternions to a single quaternion.
Yeah.
That's a projection to S4. Yeah, it's all true, but
I mean, my question is like, what does non-trivial element in this homotopy group would mean for general relativity?
I don't know.
Okay.
Don't know.
Well, thanks.
It's some global thing.
Yeah.
I have no idea.
All right. So I guess it's time to thank you again, Kirill.
Thank you.